Here we have this function of x, and we want to estimate or find this area under the graph of this function going from a to b. How we gonna do that? So again, we want to find this shaded area in red. We're gonna use something called left-hand sum or right-hand sum, LHS or right-HS. So again, what's the left-hand sum and what's the right-hand sum? It's a way to estimate the area under the curve between an endpoint or an interval. So here in this case, we have this function of t, which is increasing function, and we want to estimate the area going from a to b under the curve. Here we're gonna first use the left-hand sum. So we start to graph our rectangles in here going from the left. That's why it's called left-hand sum. So start grabbing the rectangles from the left, so going from t to the graph, the curve, and then when it hits the curve, we are going to the right, and then we repeat for rectangle 2 and rectangle b. Here, this is the summation notation of the left-hand sum. So here we have sigma going from I equal to 0 to n minus 1 of the function of ti multiplied by delta t. If we expand that term, it's gonna be of t naught multiplied by delta t plus of t1 multiplied by delta t, and so on until we reach the end term, which is of tn minus 1 multiplied by delta t. Now let's notate our t-axis and y-axis to figure out how we're gonna find these values. So starting at A, we're gonna have t naught, and then t1, t2, and at b we're gonna have t3. So here notice at A it's gonna be the same as t naught, and then at b it's gonna be the same as t3, which is gonna be equal to tn. Now for the height of the rectangle, the last rectangle is gonna be the height of tn minus 1 according to the left-hand sum. This is the last term. Here in this case, it's gonna be of t2, not of t3. Now, the first rectangle, the height gonna be of a or gonna be of t naught. Now, the width of each rectangle is gonna be represented by delta t. It's gonna be the same, and delta t gonna be b minus a, which is the endpoint over n. N is the number of subdivisions or number of rectangles in this case. Since we presented this area under the curve going from A to B by 3 rectangles, therefore n gonna be 3 in here. So what we are trying to do here, is trying to present the area under the curve from A to B by using rectangles. And then I'm gonna find the area of each rectangle by multiplying the height by the width, and then I'm gonna add all these areas to estimate the area under the curve. Now, for the right-hand sum, what we're gonna do, we're gonna start drawing our rectangles from the right side. So we are going from the t-axis until we hit the curve of t, and then going to the left, and then repeat that until we hit the curve, and we are going to the right, to the left. Now this is the summation notation. For the left-hand sum, we can see that sigma going from I equal to 1 to n of the function of ti multiplied by delta t. We expand that term, it's gonna be of t1 multiplied by delta t plus of t2 multiplied by delta t, and the last term gonna be of tn multiplied by delta t. Now let's notate our t-axis and the y-axis to figure out how to find these values in the summation notation. So at A we have t naught, and then t1, t2, and t3, not t4. So notice at A it's gonna be t naught, and then at B we're gonna have t3, which equal to tn. So now for the height of the rectangle, the height of the last rectangle, since we draw it from the left going to the right, we have f of tn, which is the last term in the summation notation, here and gonna be 4. And then for the first rectangle, it's not going to be f of t naught. It's going to be f of t1, since we are starting from t1. And then the width here gonna presented by delta t. It's gonna be fixed for each rectangle here, going from A to B. Delta t gonna be the same, going from B to A over n, where n again is the number of subdivisions going from A to B, which is the same as saying number of rectangles. Here we have 3 rectangles presenting the area under the curve, therefore n gonna be 3. So here what we are doing, we are presenting the area by drawing these rectangles, and then I'm gonna find the area of each rectangle, and then I'm gonna add them to estimate the area under the curve of f of t going from A to B. Now here notice we have 2 cases. First case, the top case gonna be when the function f of t is increasing, and then the bottom case is when f of t is decreasing. And then for each case I'm gonna notate what's the left hand sum and what's the right hand sum. For the first case, when f of t is increasing, you can see we're gonna start drawing our rectangles from the left, and for the right hand sum, I'm gonna start drawing our rectangles from the right. And remember, when we draw our rectangles, we're gonna hit that curve, and then we're gonna move to the left or the right comparing to what we are doing, if it's left hand sum or right hand sum. So for the left hand sum, when f of t is increasing, notice this area in blue. This area is missing since we are only finding the area of the rectangle, and this area is below the graph of f of t. Therefore, this is called underestimate. And then for the right hand sum, this area gonna be included in the estimation, and this is not the area under the curve, it's above the curve. Therefore, this is overestimate. And the same thing for f of t is decreasing on the left hand sum. This area will be added, therefore this is called overestimate. And for the right hand sum, this area in blue will not be included in our estimation, so we are missing these areas, therefore this is called an underestimate approximation. So when f of t is increasing, the left hand sum gonna be underestimate, the right hand sum gonna be overestimate, and when f of t is decreasing, the left hand sum gonna be overestimate, and the right hand sum gonna be underestimate. So what does it mean to be under or overestimate? Again, overestimate gonna be including more areas than the actual area, and underestimate means we are including less area than the actual area. So here in orange, you can notice this is the actual area under the curve, and we can notice that the blue color of missing or including more areas. So here we have this definition of f is continuous for the interval of t going from a to b, then the definite integral going from a to b of f of t dt. Notice a to b, a and b called the limits of the integral, and f of t called the integrand. And then it can be, definite integral can be presented by the left hand sum and the right hand sum. So it can be written as the limit as n goes to infinity of the left hand sum, or the limit as n goes to infinity of the right hand sum. Remember, n is the number of subdivisions, so when n is large, meaning we will have so many rectangles going from A to B. That means we are increasing the accuracy of our estimations, since from the previous slide, what you can notice that we're gonna minimize the missing area or the extra areas. Now, the definite integral means it's the area under the curve. In some cases, it can be computed exactly, but for most cases, this definite integral can be computed, can be approximated numerically using a calculator or a computer. Remember, when we are doing left hand sum or right hand sum, we are estimating the area under the curve, where the definite integral is the area under the curve. So here, on the left side, we have the function f of x positive, and then a is less than b, and this can be presented by this graph. So notice we have this function of x and then the interval a to b, and then the area under the curve can be presented by capital A. So now when we take the definite integral from a to b of the function of x, it's gonna be just the area. This is just the definition. Now on the right side, the function of x is negative. So it can be presented by this graph. Notice here a is positive. The area is always positive, but when we take the integral going from a to b of this function, a gonna be negative. That just means the area is below the x-axis. So when definite integral is positive, meaning the area is above the x-axis, and when definite integral is negative, it means the area is under the x-axis. Here on the left side, we have this function sine x squared, and you can see the graph. We are going from, on the x-axis, we are going from 0 to the square root of 2 and we are giving two areas. So the first area can be presented by a1 going from x equal to 0 to square root of pi, and the second area a2 going from the x-axis of square root of pi to square root of 2 pi. So now when we take the definite integral from this function going from 0 to the square root of 2 pi, we're gonna have a1 minus a2. a1 is positive because it's above the x-axis, and a2 is negative because it's below the x-axis. So when we subtract these two areas, we're gonna have a positive number. That means we will have more positive area than negative area. Here on the right side, we have this function x squared minus 1, and we can notice it's going from -1 to 1 and the whole negative given by a, but notice it's below the x-axis. So now when we take the definite integral going from -1 to 1 of this function x squared minus 1, it's gonna be minus a, so negative the area. Why it's negative? It's because it's below the x-axis. And notice here, area is always positive, but when the definite integral is negative, that just means the area is below the x-axis. Here we have this function of t equal to 1 over t. You can see that in the blue color. And we want to approximate the area going from 1 to 2 of this function. This is the same as saying we want to approximate the definite integral going from 1 to 2 of the function 1 over t dt. So for the first case, we have n equal to 2. That means we're going to present this by two rectangles. So we can see this is the graph of 1 over t, and then we have the left-hand sum in green, and then the right-hand sum in black. We can notice here the function is decreasing. So the left-hand sum gonna be overestimate and the left-hand sum gonna be underestimate. And the area gonna be between these left-hand sum and right-hand sum. For the second case, we have n equal to 10. That means now we have 10 rectangles presented the area under the graph of 1 over t going from 1 to 2. Now, notice here we have larger n, therefore we have more accuracy, since we're gonna minimize these extra areas or these missing areas. And then for the third case, remember the definite integral is the shaded area. It's exactly the shaded area here going from 1 to 2. Here we have n equal to 250, and then using a computer, the left hand sum gonna be 0.6941, and then the right hand sum gonna be 0.6921. And then if we take the average of these gonna be approximated to the definite integral. We are increasing the accuracy of our approximation as n gets larger, since we are minimizing the areas of the left hand sum that is above the graph, and then we are also minimizing the areas that are missing under the graph in the case of right hand sum. Here we have this definite integral from -1 to 1 of square root of 1 minus x squared dx. A, interrupt the integral as an area, find the exact area. So here, the definite integral is the same as the area under the graph. Here we have f of x equal to the square root of 1 minus x squared between -1 and 1. Now, if we set the square root of 1 minus x squared to y, and then arrange these terms, we'll end up with y squared plus x squared equal to 1. This is an equation of a circle with a radius of 1. However, the given function is square root of 1 minus x squared. This is a positive. That just means this is the top half of the circle. So, to graph this function, adjust the top half of a circle going from -1 to 1 with a radius of 1. So, the definite integral here gonna just be the area under the curve. Here, the area of the top half of the circle. So, what's the area of the top half of the circle? Gonna be half multiplied by the area of the circle. Half because this is half of a circle. And then the area of the circle gonna be by r squared. Remember, radius is 1 in here, so we'll end up with pi over 2. That's the area. Now this can be approximated as 1.5708. Now for b, estimate the integral using computer or calculator. Here when we plug that into a computer, the definite integral gonna be approximated as 1.5708. And we can see we are very close to the answer in part A when we have the exact area.